Hey Josh, how are you? You can't see my eyes. I'm hiding behind my wife's hat
Well, it
since
probably at
last
least
week.
it blocks the sun out.
There's no sun here. This is blocking the sun out already. I don't know why I'm still blocking it out, but I'm just trying to be less embarrassed by embarrassing myself a lot more. I know what I'm talking about, so why don't we just go ahead to the
Okay,
whatever you.
okay. So today, it should be a fairly simple problem for you, but it's a little bit more complex than what we've done in the past. So let me
Oh,
go ahead and set up the problem so you can see my screen, right?
okay. What do you have there? Like
Okay, hold on a second.
baseball pitcher on the top of a building.
A baseball pitcher. Maybe
Yeah,
the
let
maybe the
yeah,
hat is
maybe the
blocking your
catcher.
vision.
It's a catcher.
Oh, because his hand's so
Yeah,
big.
yeah, his hands are huge. I assume that's a building, or it's just a really, really large basket or something.
Yes, so this is Bob the construction worker standing on top of a building. And
Okay,
then Bob, it's just his hand. His hand is just a little big compared to the rest of his body. It's not a catcher's mitt.
okay. I thought he's
But
wearing a catcher.
he's using a hammer to do his construction.
Right.
And the problem is that Bob has just dropped his hammer. And Joe is standing at the bottom of the building and has the potential to be hit by the falling hammer.
Okay.
So the question is, how long does Joe have to get spot the hammer falling, realizes that he's about to be hit in the head, and then run away in time that the hammer doesn't actually kill him? So that's what you have to figure out is how long does Joe have to move before the hammer hits him in the head?
Okay. And how
So
high?
the information that you need is from Joe's head to the hammer is 130 meters.
Okay. Come on, you gotta give me more challenging problems than that.
Okay, let's see.
All
Let's
right,
see
let me.
how smart you really are with your PhD.
All right, it's called permanent head damage. What's the reason for that? Maybe someone dropped a hammer on my head there. But anyways, why don't you let me share my screen and I'm going to show you the calculations that I do. They're very sophisticated, complicated
Okay, go ahead.
calculation. And I'm going to draw your picture better than you have it.
Yeah, I'm pretty sure you're not going to draw it better than my simulation.
Whatever you say, man.
Yeah,
Oh,
that's
crap.
already worse. You
That
lose.
building. No, no, no. I'm not losing yet. Okay. That building's there. And then I'm going to draw Bob right here. Actually, I'm just call that Derek. I'm going to drop a hammer on your head. That's my big hammer.
Just make sure that when he drops the hammer, it doesn't clip the edge of the building and throw off the trajectory.
Wait, 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 wait. I have to draw you more accurately.
Oh, be
I have
nice,
to draw.
be nice.
You have a big head.
Oh, that's not nice.
All right, and that's you, Josh. Just changing the names here. So how high you say again? It's
130 meters.
130 meters. We're supposed to be mean to each other. 130 meters. Okay, so what we have is like an object free falling in a gravitational field G. For ease of calculation, just take G is 10 meters per second squared. I should be able to decide, did I add an initial velocity to it, right? All right, I'll
Oh,
be nice.
if you want to add one, I can add it in.
I'll just say V initial.
All the
Initial velocity.
assumptions are up to you.
Yeah, because I'm deliberately dropping it, so I'm just gonna hold it and then I'm gonna drop the hammer.
Just make sure you don't force your hand down and add some initial velocity.
No, I won't. It's okay. I'm just gonna let go. It's pretty easy. All right. So in this problem, we know that this is the acceleration that the hammer will experience, right? What we'll do is So I can remember the equation. I'm not going to derive it. Okay. The height, let's call it y, is equal to the initial velocity t times the time plus 1/2 at squared. Gosh, you got to give me a more challenging question. This is so easy. So we have the initial velocity here, and then this is our acceleration. So let me write that initial velocity. Okay, and then this is the acceleration. And then this is the time, right? This is the time.
And
These two,
that's what you have to find is the time, the
that's
t.
what I have to find, right? I'm trying to find out whether Josh can get away in time before Derek drops the hammer on his head and gives him a PhD.
But Josh is really fast.
Oh, but Josh already has a PhD. We can get two PhDs.
Yeah,
But
I don't need another one.
just a permanent head damage, you know. Two permanent head damages versus one. So I mean, this is easy. Come on. You gotta give something more challenging next time. So the height we know is 130 meters, and that should equal the initial velocity is 0 times the time plus 1/2. Um, the acceleration, I'm just gonna use 10 seconds squared, then times the time. So I mean, sometimes we use this negative, but I'm just going to define the direction going down as positive. So that's it. So I have 130 meters should equal 1/2 times 10. Oops, let
Yeah,
me
don't forget your squared under t.
don't forget the squared on the t, and don't forget my units. E, okay, and squared. So all I have to do now, 2 times 130 is 260. 260 divided by 10 is 26. So I have 26. And units of meters cancel out. I have second squared over here. So equal t squared. It's just going to be the square root of 26. And I take the second squared out of the square root. I have square root 26 seconds, which is about 5 point, I think 5.05 maybe 6 5 point, oh, so 5.09 seconds. Took
And
me like what,
you
two
can do
minutes?
the square root of 26 in your head.
Yeah, we're Asians, we can do any
That's
square.
pretty magical.
I know. I just did it again in my head.
Okay, so this is your answer is 5.09 seconds.
Yeah, I'm pretty sure that's correct. Well, let's see your simulation then. Let's see how
Okay,
it.
so let's go back and let's run the simulation and see if your answer is correct.
All right, sure.
Okay, so let me first account for your 10 meters per second squared.
Okay.
So that's your assumption about gravity.
Yes.
And now I'm going to drop the hammer
Drop
and
it.
see what happens.
Okay. Oh, that's a slow hammer. What? It's your simulation speed. Why is it going so slow?
Let me speed it up a little bit. It's a little bit faster.
Oh, it takes how long?
And
20?
it takes,
What
looks
the?
like about 34.6 seconds.
You added
You
some
said what,
friction.
5 seconds? And it's 35 seconds?
You added some friction in there,
This
man.
is not very. This PhD is not benefiting you very much.
I'm giving you the PhD. It hit your head.
I'm still standing, so I have a hard head.
I know you do. So what did you do there, man? Come
What do you mean?
on.
I didn't do anything. I just dropped the hammer. Initial velocity is 0.
Right. But how could the, you have that classic that you have a drag. That is the terminal velocity. That's called the terminal velocity.
This?
Yeah.
Oh.
You have an air drag.
Oh, Mr. Smarty Pants.
I
Okay, so
do.
now you happy? I turned the drag off. Now let's see
Right.
if your theory is correct.
Yeah, you got me there, man.
Oh, it's a little bit faster that time.
Yeah,
So 5.07 seconds. Oh, very
like
smart, very smart.
oh, and this time you fell down too. Look at that.
Mm. Because it hit me a lot harder. My head's not that hard.
Okay. Okay, in the real world, please don't do this at home.
So
Please don't try.
you can see I have a v squared term that's affecting the speed of the hammer, and so it just took a little bit longer.
Gosh, you trolled me there.
Yeah, but
You
at
really.
least you're smart enough to figure out a hit terminal velocity.
I almost thought that I had the wrong calculation, but I looked at your graph and I said, "Oh, okay, up right there. That's clearly something." You're a
Very
smart
very
guy,
good diagnosis.
but you're a smart guy. You like freaking tricked me there. I
Sometimes you gotta throw a little bit of a loop. Helps you learn a little bit more.
well, yeah, that was actually fun. Though. So I win this time.
Yeah, I mean I guess you're partially correct.
What do you mean partially?
You,
I
but
was
you didn't. When you set up a problem, you have to state your assumptions, and one of your assumption was not that there is no drag.
oh yeah. That is true. I mean, but air friction is not that bad, right? I mean, like how
Well, I mean, it may have been artificially set high by the designer, but
right by Josh himself, and that actually saved your head, right? And the
well,
hammer hit
I was
you.
trying to give myself a little bit more time to get out from under the hammer before it hit me.
Yeah, 30 seconds is an awful lot of time.
Yeah, it's plenty of time.
That was kind of fun. Actually, that's a very nice graphic too, by the way. Gotta say that. Gotta give you that. And I think
My
that
Algodoo skills are improving slowly.
I need to catch up to you.
You'll get
So
there, don't worry.
yeah, for our next video, I'll give you something fun
Okay.
and something unexpected.
Okay, let's see.
That was fun, man. Thanks a bunch. Okay, man. I'll see you next time.
Okay.